Okay.
Jared's in trouble.
Thank you. So this unit goes along with chapter 3, so that's like one of your first homework assignments, right?
Do we have homework for tonight?
To read chapter 3, but just the projectile motion part, because chapter 3 goes into vectors and projectile motion, and we're going to start with projectile motion. So you guys just read those pages. I'll try and post those specific pages on the web. But today we're just looking at projectile motion.
Will we watch the question video?
Yeah, we have to watch it on my computer though, because the projector is like dead.
Does it have to do with like
It does, yeah.
Mythbusters? Oh, Mythbusters.
Yeah.
I was thinking Ghostbusters.
No. Okay, so projectile motion in general just means anytime something is moving in 2 dimensions. So we did linear motion last, which is just if something's moving in a straight line. So this is if something is moving in 2 dimensions. So like a football being thrown, or if I knock the expo marker across the room, that's projectile motion, right? Anything that's that has like an x displacement and a y displacement. Does that make sense? Okay. And projectile motion specifically also means anything that is in free fall. So that means that no other forces are acting on it other than gravity. So after the football is released, right, the only force that's acting on it is gravity. After my hand stops, smacking the expo marker, the only thing that's acting on it is gravity. So when something is in free fall, the only acceleration it experiences is the acceleration due to gravity. That only affects its y components. So that's one of the strategies that you'll see that we use with projectile motion is we break it into like x and y dimensions, and we treat those almost separately. So we're going to start getting into like some of the trig stuff to do our cosine, sine, and look at our x and y components. Okay, so what this means is it has like really, really important implications for projectile motion. What it means is if something is experiencing projectile motion, its horizontal velocity stays the same the whole time. So if I knock, the expo marker off the table, it has an x velocity and a y velocity. Its y velocity will change because gravity is accelerating it towards the ground, but its x velocity stays constant. Okay, and that's like super important for projectile motion. And another thing is the x and y are independent of each other. So it actually doesn't matter whether I knock my expo marker across the table or if I drop it. They're both going to land at the same time. And this is like super hard to actually do in real life, where you like have it dropped and try. Okay. Is that, no? Yeah. I messed that up. So it's really hard to do in real life, but you'll see on your notes, there's like a little chart that shows the position of a ball that's being dropped versus the one that's being projected. And they will fall at the same rate. So they both hit the ground at the same time. The only difference is the ball that was projected now has some x displacement. So it's further away from the starting point.
Wait, so like if you throw a football as hard as you can, like straight, it'll hit. How will that hit the ground at the same time as it like
a football being dropped?
Yeah.
Yeah, I mean it's hard to believe, right?
Yeah.
Well, usually you throw footballs up, right? You don't throw them perfectly horizontally. But if you threw a football perfectly horizontally, it would land at the same time as a football being dropped. And I know this is so unbelievable. That's why I have the Mythbusters video I wanted to show you guys, which hopefully we'll look at the end of class, they did this, and they did it with like the most extreme projectile you could think of. They used like a gun and a bullet. So they dropped a bullet, and they had like they had the whole like rig set up so that the timing device of the one being dropped at the very same time as the one being fired out of the gun. So they fired one out of the gun and they dropped one, and they hit at the same time, and they like caught it on the like time lapse camera. So we'll look at that at the very end of class. I know it's hard to believe, but it's true. And that's because the X and the Y are totally independent of each other, and so their Y's are the same, right? Their Y's, because if you're hitting something horizontally off of the table, right? Initially it has no Y velocity, right? Its initial velocity is all horizontal. So that's the same as something starting from just being dropped. They both have a Y initial velocity of 0, and then they're both accelerated by gravity now.
Do they both have to be at like the same height?
Yeah, they have to be at the same height. Yeah, it can't be just like any old situation.
Now would the trouble in this come in where like you fire or like throw football at like an angle?
Yeah, so if I throw a football at an angle, like up at an angle, or throw a football up at an angle, then that's obviously going to be different. But we still can treat the X and the Y separately. So we'll see all those examples today, hopefully in our notes. But just, I guess, believe me for now, and we'll see the Mythbusters in a second. They'll prove it. Okay, so remember, we've been dealing with vector quantities. We know velocity is a vector quantity, meaning that it has a direction. And that's going to become super important in projectile motion because we need to break our velocity into X and Y components. And so we do that using trig. So we take our whatever our velocity is at whatever angle it is, and we break that down into the X and the Y component. So you see like the little triangle here. And so the X component is going to be the hypotenuse of that triangle. So I did, because I made these notes. They draw it like this. Where this is Vy, this is Vx, and this is the hypotenuse, or we call it the resultant in physics. But you could also draw this as a right triangle. So this is really the same thing.
And V is just the distance then?
It's the velocity. V is the velocity. So we're taking the hypotenuse, and we're saying the x component of this triangle, or the x component of this velocity is Vx, and that's going to be given by V cosine theta. This is theta.
What does Vx represent?
And then this is Vy, which is V sine theta, right? And that just comes from the definitions of cosine and sine, right? So Katoa, cosine is adjacent over hypotenuse. So if I'm solving for Vx, I get V cosine theta. And same thing for sine, right? So opposite over hypotenuse.
Does that say just cosine equals Vx over?
Cosine theta.
Okay.
I squeezed the theta in there.
Yeah, but what does Vx
Can we just write X?
What does Vx represent? It represents the x component of the velocity. So like if you throw your
Average
football,
velocity or like starting velocity?
instantaneous velocity. So it could be the velocity at any point. Frequently use it as like the initial velocity. So if I'm taking my football and I'm throwing it at some angle, it's going to have an initial velocity that's at an angle, right? So that would represent this hypotenuse, this V.
And then the cosine of theta would then cancel out how far it would do the math like hard for like how long it would take to drop it. No,
No.
for how far it would travel on the x-axis.
No. The Vx and the Vy just give you the x and the y components of that initial instantaneous velocity. So they're just saying like what's that initial x velocity or the initial y velocity.
So, like, the Vx velocity would be like the velocity that it's moving straight this way.
Yes.
And then the Vy velocity would be like the
Up.
velocity of it moving up.
Or down.
And then
Yeah. If we're like throwing.
just V is just the velocity of
Yeah.
wherever it's moving.
Yep. Exactly. Okay, so then once we resolve our situation into like the x and the y and we separate those, then you can use your normal linear motion equations. So you'll see that all the equations in here that we're going to use are the same ones that you use in linear motion. We're just doing like linear motion in the x and then like x and then linear motion in the y. We're treating those like separately. And the x is super easy because you guys might remember I said that x velocity doesn't change. So there's no like initial or final velocity. It's constant velocity. So the only equation that we use is that the displacement equals the velocity times the time. So you'll see like these are all your equations for your vertical and your horizontal. And the only thing that's the same between these two is time. So like time you'll see as we get into some examples is like the big connector between horizontal and vertical. Sophie, you have a question?
Yeah, the Vx and Vy on this sheet are reversed from those two. But
Oh yeah, that's a
is
mistake.
that okay?
Total mistake.
Cool.
Yeah, so fix that on your note sheet. Thank you, Sophie. Fix that on your note sheet. The horizontal is the x and the vertical is the y. Might be.
That's what I got.
What do you-
Okay, never mind.
Oh, it's on the
It's
chart.
Oh.
Okay, so let's take a look at an example. So all the examples, and then all the previous assumptions that we made about linear motion are going to be the same. So if we're looking at the full arc of something, so this triangle really only represents that
Oh man, this gets so complicated.
that instantaneous velocity, that initial velocity. So if we're talking about our football, right, it's going to make an arc like this. All right, so all of the assumptions that we've previously like held in linear motion are still going to be true. So our vertical velocity here, Vy at the top of our arc is 0. Our velocities at the same place in our arc are going to be the same. So whatever, just opposite signs. So whatever the velocity is here, call that A, is going to be the same as the velocity here, right, at the same height. They're just going to be opposite. So if this is like 30 degrees, so if VA is like, 10 meters per second at 30 degrees, this one's going to be 10 meters per second at negative 30 degrees. So before when we had linear motion, since it was only like, you could only be left or right or up or down, right, we just said like positive and negative to indicate the direction. For projectile motion, we have to use an angle to indicate the direction because it's 360, right?
So when you say like 10 meters per second, how do you know what point they're talking about? Like, are you just assuming it's release time?
Well, yeah, I mean, it depends on your problem. They have to give you more information. They have to say like,
They wouldn't just say
They
it
would-
moves
yeah.
10 meters per
So
second.
does that, what's it say at the end? It said V, like the point at the end of the dotted line, it said like V something.
B,
VB.
yeah.
Sorry,
So
what
that's
is
just
it?
at the same place in the arc,
Uh-huh.
they'll have the same magnitude of velocity, just opposite direction. Just like in linear motion, right? If we said like something goes up and then it goes down, it takes the same amount of time going up as it takes going down.
Oh.
And like if it initially is like 10 meters per second launched up, it's gonna, when it gets back to that same point, it'll also be at 10 meters per second. And before we said positive 10 and then like negative 10.
Uh-huh.
Now if it's at an angle, so if it's 10 at 30 degrees, it's now going to be 10 at negative 30 degrees
Oh,
at the same point. So the angle is now what's giving us our direction.
It makes a triangle, like whenever you throw a ball.
I think so, because it is quadratic, right? Times squared.
Sure. No, I'm not quite sure.
S equals VOT plus 1/2 AT squared.
You want to slow it
Is it
down.
quadratic?
Why did you
It really does
Say-
feel like a Monday.
why is
Yeah.
it changed out for 0? O is just 0.
Yeah,
Why-
O is 0,
we should-
yeah.
We should never include that. In
O
the
is
dictionary
0,
because it's
I
completely
is,
pointless, right? Like
what?
What is
if
O?
it's 0,
O?
the 0. When
Your initial velocity is not always 0.
No, but when it's 0. But when they say 0,
Oh,
O
in
is
the
0.
in the equation, in the equations they give you here, they're using sometimes they like use 0 and like final, like O and final, O and F. So 0 meaning initial, or they use I, or they use 1. So like situation 1, situation 2, right? You guys are always deciding like what your two snapshots are. So you're always deciding like what's my initial, what's my final.
Yeah, but if it's 0, then it doesn't matter.
Well, the 0 doesn't indicate that it's 0 here.
But
The
it's
0. Yes, the initial velocity is sometimes 0. But the 0 in the symbol here in the equation means initial velocity, not like 0 velocity. Okay, so let's take a look at an example. So this is example 1 on the back of your sheet. How far away from the cliff can an object travel before hitting the ground if it is launched with a speed of 5 meters per second horizontally off a cliff, which is 100 meters high? So if it's asking how far away from the cliff, it means horizontal displacement. It wants to know, because it already knows what the vertical displacement is, right? Because we know how tall the cliff is. So it's asking how far away horizontally.
We don't know how far away he is.
Who?
Wait, how far?
He. How he knows a he? What if it's she?
But something's launched.
It's a cat.
What is the cat launching itself off the cliff?
We don't know.
But there's going to be an extra height if there's a person launching something off the cliff.
We're assuming, we gotta assume that it's perfectly at 100 meters.
Alright. It's inaccurate, but I'll go with it.
Oops, not 100 meters, like that. 100 meters. Okay, so the cliff is 100 meters tall, and our initial velocity, which is, it says horizontally, launched horizontally. So our initial velocity is all x, is going to be 5 meters per second. Okay, so in terms of like our good problem solving practices, I've drawn a picture. What do I need to do next?
Do the thing and then plus minus. I don't know what it's
Label your coordinate system.
called. Yeah.
Okay, so I'm going to do a normal coordinate system where up is positive and to the right is positive. And then what do I do normally?
This way.
List your variables, okay. And so this is where things are a little bit different for projectile motion. You're going to list y and x, all right? So we have 5 variables for y, because that's like our normal linear motion thing. So we have VIY, we have VFY, or you could say 1 or 2, or 0 and F, or 0 and 2, or 0 and 1, right? It doesn't matter what you use, just that you're indicating that these are like 2 different snapshots. So for us, right, this is our initial conditions up here,
So,
and then this is our final conditions here.
so would VIY be 0?
VIY is 0, yes, because my initial velocity is entirely horizontal. So this is essentially the same in the y plane as dropping the ball. But now it's going to go some x distance, and I want to know what that x distance is. Okay, so VFY, I don't know. SY, we know, is,
Wait, what's that?
100
Oh,
meters.
SX.
careful. Look at how I've defined my coordinate system.
Negative.
It's negative 100 meters. Just because it's a down is negative.
Okay.
The acceleration in the y direction is
Negative 9.
negative 9.8. That's just from g. And then the last variable is time, which I don't know. Okay, and then the x, we have vx, which is 5 Time we don't know, and x displacement we don't know. And
So
that's
we're
what,
not doing like an initial and final velocity for x.
well, they're the same.
Oh right, because it's just going straight.
Well, the horizontal, there's no acceleration in the horizontal direction, right? Gravity always pulls things down towards Earth.
So if I throw a ball straight, it's gonna be moving at the same speed the whole time.
Horizontally.
Yeah.
Don't you?
Its velocity will change, but its x component of that velocity will not change. So the y component is changing,
Yeah.
but
But-
the x does not change.
So, but if I don't throw it straight, I throw it up a little bit, then
X component doesn't change.
Does that apply to all of them? Like any problem that the x doesn't change
Anything
and the
that's
y
in
does?
free fall. So anything that's only under the power of gravity. John, you had a question.
Then isn't time the only thing that matters?
So time is the important thing here, because if we're looking for x displacement, right, we only have one equation in the x direction, right? That's Sx equals Vxt, and Sx is what I'm looking for. I have Vx, but I don't have t.
So you have to find t from y.
So you have to find t from y, and then plug it into there. And that's like a really, really common thing that you're going to see in these types of problems. Okay, so we want.
Should we use the second equation then?
So yeah, the second equation is a good one for us because it doesn't have final velocity. So I don't have final velocity, and I don't care about final velocity. So I'll use my second equation, which is Sy equals Vyot plus 1/2 squared. And the good news is this is 0. So I don't have to deal with the quadratic formula. So I have 100, negative 100 equals 1/2 negative 9.8.
wait, Vy,
squared.
that's just velocity y. Does that not specify all for like if it's velocity initial or final?
Oh yeah, that's 0. So I'm switching back and forth between initial and 0 and 1 and 2, so sorry. Your book does it one way, I learned
So
it another
the
way.
0 is a 0.
The 0 is 0 in this
I was right.
case. No, John,
You're not.
you were not right because V0 is not always 0. In this particular case, you're right because V0 is 0. But the symbol V0 means initial velocity.
But it means like when it hits the ground.
No, it means initial velocity, whatever that means in your scenario.
Alright.
So if I chuck an expo marker
Up and then off the cliff, then it would not be 0.
up and off the cliff, yeah, or if I like chuck it at an angle down the cliff, right? If it has any angle other than 180 degrees or 0 degrees, then it's going to have a y component to its velocity. Okay, so what do we get for time here? Make sure you take the square root.
I don't know.
Okay. Like 4.52.
Yep. So I got like 4.51753 seconds. And I'm keeping a lot of extra digits in here because I know this is not my final answer, right? So I don't want to apply my significant figures yet. So I'm going to plug that into my other equation so that now I can say Sx equals Vx, which is 5 meters per second, times 4.15. So what is my x displacement? Should be a little more than 20, right?
22.6.
22.587. And then how many significant figures do I need? 3.
Yeah, 3.
So 22.6. Final answer? questions about that? Okay, so you can start to see like how we're treating the x and the y components separately.
The times would be the same because we're talking about like the same ball and
Yeah.
it would end up the same. Okay.
Yeah, so it takes us, however long it takes to ball that distance, it takes the same amount of time to have that x
Will
displacement.
Tx and Ty always be the same?
There is no such thing as Tx and Ty because they all are always the same because we're talking about one object, right? Okay, so then looking at the second example, now we have an angle, so we do have an initial y velocity, so you'll see how we use the component thingy. So example 2 says, how far can an object travel if it is launched with a speed of 5 meters per second at an angle of 36.9 degrees above the horizontal, assuming it ends at the same height at which it began. So 36.9 degrees. VI is 5 meters per second again. This is gonna
It's so tiny.
this. And I want to know this. I want to know the x displacement. And it says ending at the same height at which it began. That's an important piece of information. Define my coordinate system. I, x, VI, y, VI, VF, y, SY, T, AY, VX, T, S, X.
And why is there no like velocity initial or velocity final for x?
That's because it's at a constant velocity. So the initial is the same as the final.
Always?
And there's no horizontal acceleration. Yeah, because think about like if you're throwing a ball, what force is accelerating it in the horizontal direction?
Like, whatever launched it.
Alright. So your hand,
I mean it's not accelerating, is it?
it's not accelerating. That's the point, right? Is that there's no acceleration has to be caused by a force, right?
Yeah.
So if I'm throwing something, after it leaves my hand, it's in free fall. The only force that's acting on it is gravity. My hand is no longer forcing the ball to do anything in the horizontal direction. So it's going to stay at that same horizontal velocity, whatever it is. Okay, so this is where we need to break this initial velocity down into
You
its
didn't do it.
x. Oh no, I can call it.
Yeah.
I told him about the phone. Okay, I'll take care of
What's
it later.
delta velocity and y?
Well, actually, here, I'll just do it right now, because I got really cut. They like called me in the camera. Who was there? Are all my juniors here?
I don't know how to really use this video because I cannot learn anything without being able to ask questions. At all.
Okay. So this is where, maybe I'll do that next time. This is where we do have to break this into the x and the y components. So that would look, here's the x component. Here's the y component of that initial velocity. So for the y component, that's going to be VI sine theta. And x is going to be VI cosine theta.
Is the
So
way that,
wouldn't it be 5?
yeah, you got it.
VI is 5.
Oh, so that's for both. So now
So
we're
this
starting
one-
with information on the y instead of information on the x. Like last time,
Well, we have both.
Oh.
We have this initial velocity as an angle, right? So that means it has an
Oh.
x component and a y component, right? As represented by this triangle.
Oh yeah, I just meant
So-
like how in the last one we said the vx was 5.
Uh-huh.
Like because it said it started with 5, we said that was the x. Like how do you know whether it's actually y?
It's both. It's at an angle.
So like vi cosine theta is equal to 5.
Nope. The initial velocity is the hypotenuse of the triangle.
Okay.
So the x component is going to be 5 cosine theta. So 5 cosine 36.9. And then the y is going to be 5 sine theta.
Okay.
We don't know the final y velocity. What about the y displacement from here to here?
Isn't it 0?
Very good. Yeah, it's 0. Overall, there is no displacement in the y direction.
So is the way to solve this?
Oh, it's
Because it's because it
Because it-
starts at the same point.
It does
Yeah.
elevate, but it
Yeah.
goes.
Yeah, but the displacement, right? The distance would be different, but the displacement is 0.
And
Is
then
the-
don't we know the acceleration?
Yeah, acceleration is
9.8.
negative 9.8 meters per second squared. And then John, you had something to add?
Yeah, is the way to solve this to have initial velocity of y times time will be the negative 1/2 acceleration y times.
Then you're using the second equation,
Yeah.
right? Yes.
Is that because that's the way to solve this?
We will use the second equation. So this one is like, now it's almost similar, or it is similar, to our previous example in which we're going to solve for time, plug it into my other equation to get the x displacement. But this time we do have that initial velocity. We just don't have the constant term. So this looks like our equation is sy equals vi t plus 1/2 ayt squared. So that's 0 equals 5 sine 36.9 meters per second t plus 1/2 negative 9.8 meters per second t squared.
So you just plug in the 5 times the sine of 36.
Yeah, and make sure that you're in degree mode, especially those of you who are
Oh,
in
yeah.
pre-calc.
Or
I'm
calculus,
sorry.
because we're in
Yeah,
radio.
Are you in radio mode too? I'm so sorry. Like,
I'm
make
refusing
sure,
to go to radiance.
make sure. Yeah, that's fine.
It's
That's
so
fine with
weird. The whole
me. Fight the power.
Yeah.
Fight the man.
Oh, we're not gonna have time for that.
Stick with degrees.
Last year on my pre-calc exam, I did half of the exam in like the wrong mode instead of reading.
Yeah,
What does it even
I had a
do?
student do that last year on the midterm for the physics exam, and then they were like,
What does it even do though? Like, I don't understand.
radians?
Yeah.
Ask your pre-calc teacher or calc
Well, no, I know like the radians degrees. I just don't.
It's like a formula
just
designed
a
to like
calculator.
confuse math,
No, it's just
so that they
so
have
it's-
something
it's
else to
related
teach
pi
after you
to-
pass algebra 2.
Getting pi to the radius in a circle.
Yeah, I know
Should we
that,
finish
but
this
it's
problem?
weird how it does it on.
Yeah.
Okay. So, since I don't have a constant term here, I actually can factor this equation. I can factor a t out, and that gives me t times 5 sine 36.9 plus 1/2 negative 9.8 t. So I have two answers for this, right? This still equals 0. So the two answers are when t equals 0 and when this whole thing equals 0. Which should make sense, right? Because I said my y displacement was 0. There are two places that occurs. At the very beginning,
Which is when time is.
which is when time is 0, and then at the point where I want to know what it is. And that's after it's done its projectile thingy. And if you solve for this, because acceleration is negative, we've defined acceleration as negative, you'll get a negative time, but that obviously doesn't make any sense, so you just make it positive, right? The only reason you get a negative answer here is because we've assigned the acceleration as negative. So we get 5 sine 36.9 plus 1/2 blah 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 equals 0, which gives you a time of
It's a short one. 0.61. The only way that I know how to solve this is by guessing and check.
that can't be true.
But I got 0.6115.
Oh, that's wrong.
60. Yeah, see, that's why it's the problem.
You should learn how to do it and not
I
just
know,
guess and
right?
check.
I know.
This is how you do it.
How do you do that?
Well, this is a linear equation now. This is a number plus a number times t equals 0. So this is the equivalent of 5 plus 2x equals 0. Right, so we would move this constant to the other side, divide by the coefficient of our variable, and then we'd solve it. It's just that these numbers are like
But that's the time.
messier. That's the time.
Well, so.
Tom.
What happened? Oh, you factored out. Okay.
Mhm.
I see.
What did we need velocity x for?
Yeah, multiply that by the time.
What do we need velocity x for?
Like, when did we use it
We haven't used it yet. We haven't solved our problem.
Oh, I forgot.
I know, it's such a long process. You're like, okay, I got an answer. And this happens to people too, where you're like, you solve your equation, you get something, and you're like, oh, good. Ah, but it's not your answer, right? We haven't answered the question being asked, right? What they asked was, how far can the object travel, blah, 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 blah. So that's gonna be now sx equals dx times t. So now we can say sx equals 5 cosine 36.9 times 0.612, which gives us
2.44 if it's 3 significant.
don't round your answer. 2.45.
Okay.
You must have rounded at some point.
I was guessing check.
Yeah, that's not a good strategy. So this gives you 2.45 meters. So that's how far it could travel. Oh man, we are out of time, aren't we?
Yeah.
Okay, goodbye. So we'll do the last example
And
Monday.
I'm really curious about this
Oh.
liquid now.
Yeah.